Good afternoon, everyone. On behalf of Department of Electronics Engineering, RAIT, I welcome you all for today's third session of our ATAL FDP on robotics. As said by Alan Kay, the best way to predict the future is to invent it. It is hard to imagine modern telescope without any robotic features. We have now entered the era of telescopes from afar, and robotic telescopes are revolutionizing outer space research. It is my proud pleasure to welcome our esteemed speaker of today's session, Dr. T.S. Kumar. Currently, sir is working as Engineer E, Aryabhatta Research Institute of Observational Sciences, ARIES, Nainital, India. He is Chairman, ARIES Engineering Division and Electronics Engineer in charge for 3.6 meter Devasthal Optical Telescope, ARIES. Sir has completed PhD in Systems and Control Engineering from IIT Bombay, India in August 2015. He has total research experience of 14 years. He has handled design and development of different projects such as back-end instruments of 30-meter telescope TMT, ARIES Devasthal Faint Object Spectrograph Camera, total solar eclipse expedition on March 29, 2006 in Turkey, to name a few. He has received a number of awards and grants at national and international level. He has also delivered number of talks. He is member of various organizations such as Indigo Consortium and India TMT Core Group. He has guided many PhD and MTech students and has more than 50 journal conference publications. His engineering expertise is in telescope electronics, control systems, and back-end instruments engineer with versatile knowledge and expertise in telescope systems, back-end instruments, distributed control systems, servo systems, mechatronics, and industrial automation. Today's title of Sir's session is Precision Imaging Using Large Ground-Based Automated Modern Optical Telescopes. Now I request you, sir, to kindly start your session. Over to you, Dr. T.S. Kumar, sir. Thank you.
Thank you very much for the kind introduction. I am, as it was mentioned, I am T.S. Kumar. I am from Aryabhatta Research Institute. We are located in a place called Nainital in the lower Himalayan range, north of India. And we do research in both astronomy and atmospheric sciences. So we have several telescopes and also national radar facility here for the atmospheric profiling, wind profiling, etc. So we fall under Autonomous Institute under Department of Science and Technology, and we perform pure research in this area. So at the outset, I would also like to extend my thanks to Dr. Vishwesh and Dr. Prasid for contacting me and giving me an opportunity to participate in this e-lecture series and interact with your fine group. So it's my pleasure. So in this presentation, I'll be discussing the precision imaging using automated ground-based modern optical telescopes. Of course, all optical telescopes used in astronomy, they are automated. They're also robots because they do all the throughout the night, they do all the corrections, they compensate all the errors automatically and provide precision images at the focal plane of the telescope. So apart from motion control, there are other important techniques used in telescope. For example, mirror control techniques like active and adaptive optics, which are very crucial for large optical telescopes. And these telescopes which have such mirror control techniques, they are called modern optical telescopes. So we'll be discussing about ground-based telescopes. They could be both radio and optical. But since we have optical telescopes here, we will be focusing on this type of telescopes. So just to give you a brief overview of optical telescopes, what are optical telescopes? These are set of optical elements. The simplest is an objective lens which collects light from distant sources and it focuses on the focal plane. So in case of astronomy telescopes, at the focal plane, a detector is used. So detector could be a CCD, large format scientific CCD imager, or a spectrograph or polarimeter for resolving the polarization in the light. So most of the astronomical telescopes have large back-end instruments, detector system, which digitize this light coming from distant sources. So these optical telescopes used in astronomy, they are very large, and normally mirrors are used. Two mirror system, which has a primary mirror, which is the main light gathering element, and a secondary mirror called M2. So most of the telescopes are two mirror system, which are used in astronomy. So why telescopes are important for astronomy? Because the astronomers want to probe the celestial objects which are embedded deep into the sky. They are very, very faint sources. And you say a 4-meter class telescope, which are there in Nainital, we have two such telescopes. They are very powerful, and they can probe objects which are fainter by even 1 million times, which a naked eye can see. So this is just a comparison, these images. So in a urban cities like Mumbai, where there is a lot of light pollution in the night, a naked eye can see only brights which have a magnitude of 2.5. So astronomers talk brightness in terms of magnitude. Sun has a minus 27 magnitude. It is very bright. So as the magnitude increases, the faintness increases. That is, the intensity reduces, and each magnitude is roughly 2.5 times fainter. So Saturn planet, which one can see, has a magnitude of 0. So this 2.5 means about 7 times fainter than Saturn. So if in a better sight, reasonably better sight, a human eye can see stars which are fainter to a limiting magnitude of 6.5. So now a beautiful Milky Way can be seen in a fairly good sight. And normally, where these large telescopes are installed, a trained eye can see up to 10 magnitude faint stars. So telescopes are installed in these special sites, which are very, very dark. So normally these are installed in very isolated mountains with altitude of minimum 2 kilometers, so that we are above the atmosphere opacity due to aerosol concentration. So beyond 2 kilometers, atmosphere is very transparent, and dark sites are required for telescopes so that there is no light pollution, and when very faint objects can be resolved. So there are these are the just a list of major telescope facilities across the globe. And recently, few years back in India, a large optical telescope was installed, which is one of the largest telescope in Asia, and that is installed in Nainital at our institute, ARIES. So these are the 4-meter class telescopes where our telescope fits in, and the second row is like 6-meter class telescope. So when we say 4-meter or 6-meter class telescope, it describes the diameter of the primary mirror, the main light gathering area of the telescope. The largest single mirror which can be manufactured due to technology limitation is 8-meter. So the Keck telescopes are 10-meter telescopes. So here mirror pieces are used to they are controlled in tandem to maintain the phase coherence, etc., with an accuracy of few nanometers. So they use several 1-meter class mirrors to construct this 10-meter overall telescope. So as I said, at ARIES we have two 4-meter class telescope. One is already commissioned and functional since last few years. This has a diameter of 3.6 meter single mirror telescope. It's a 2-mirror system. As I said, 2-mirror telescopes are popular in astronomy. The secondary mirror, which folds the focus, has a diameter of 1 meter, and it's called a Ritchie-Chrétien type telescope, just for the completeness. And this is the evolution chart of the telescope over the last 60 years, 70 years. So Up till 1990, there were very few telescopes, but here the Europeans demonstrated in the new technology telescope use of mirror control system to eliminate all the aberrations which are introduced within the telescope. So you can actually make use of full potential of this telescope. And within few years, both Americans and Europeans also demonstrated adaptive optics technique because ground-based telescopes they see through the Earth's atmosphere, which is very turbulent. So to compensate Earth's atmosphere, there's one more technique, a mirror control technique called adaptive optics, which is used. So with these two techniques, the telescope utilization it revolutionized the way telescopes are used, and we can see there is a surge in demand of large telescopes now. So this is just to show you a size perspective. These are the space telescopes, Hubble Space Telescope, which was launched in early 90s and commissioned. It is a 2-meter class telescope, a diameter of 2 meter. And the new generation space telescope, which will be launched very soon, it will be having a diameter of 6 meter, James Webb Space Telescope. It will be launched, I think, in 2021. And compared to the ground-based telescopes are really very big, and three very ambitious projects are underway, where this is a 25-meter class telescope, and this is a 30-meter telescope, which will be installed in Hawaii. So in this TMT 30-meter telescope, India is one of the five big partners and actively participating in building this telescope. This is another telescope being developed by Europeans, which is having a diameter of 40 meters. So this can be compared to a large football field. So ground-based telescope, if all the techniques are used to get precision imaging, we can really have big telescopes which are at par with space-borne telescopes. So just to give you a glimpse of a major telescope in India. So a few years back, ISRO had launched a space telescope called ASTROSAT. It's a multi-wavelength experimental platform. Simultaneously, optical and high energy X-ray and gamma ray imaging can be done. Studies can be done using this space telescope. And as I said, this is that 3.6 meter telescope at our place, Nainita, which is optical telescope. And there's already a radio telescope facility near Pune called GMRT Radio Telescope Facility. This has 45-meter diameter dishes spread across several kilometers. There are 30 such dishes which are spread across this area, and this is fully indigenously developed in late 90s. So these three facilities complement each other and provides a very nice experimental platform for the astronomers within country and also abroad for doing multi-wavelength studies. So this was the introduction of different telescopes and how big could a ground-based telescope could be, and what this telescope exactly does, how it functions. So this telescope is supported on a two-axis system called large telescopes generally have altitude and azimuth axis. So the objective of the telescope is precisely point the objects in celestial sphere in sky and track it because Earth is moving. There will be a relative motion between the sources in sky and telescope. So it not only has to position itself in the sky accurately and also track the objects continuously. Because sky projects a two-dimensional image on telescope, we require at least two axes which are orthogonal to span the entire sky. So one of the axes is rotating the entire telescope along the horizontal, which is called azimuth axis, this circular thing. And there is one more axis which is orthogonal to it called altitude axis, which is nothing but the axis supported by this blue fork on which this tube is suspended. So this cartoon shows a small telescope and a tube, and this tube can move up and down using this altitude axis. so that the telescope can see at 90° and also close to the horizons. So these telescopes have to be very, very precise because the angular size of the stars are less than 1 arc second. We use notation called arc second and arc minute. So 1 degree has 60 arc minute and 1 arc minute has 60 arc second, which is equivalent to 1 arc second is equivalent to close to 5 micro radians. So the star is very, very small. So it has to precisely point this very small source and also accurately track it. And generally, the instruments like camera, which are used on this telescope, they see very, very faint sources up to 23, 24 magnitude, which are like a million times fainter than what an eye can see. So the exposure times are really very long. And especially when we do spectroscopy, the exposure times are more than an hour or so. So this has to maintain the position of the star on the focal plane of the telescope. So it has to point the track accurately and point the star accurately and track the star continuously for long hours without any user intervention. So the control system has to provide a motion for this large structure. So this telescope is really very heavy and it weighs, the moving mass of the telescope is close to 100 tons. So it has to accurately control this large structure and uses very precise encoders and direct drive motors to achieve a control accuracy of 0.05 arc second. So it's a fraction of microradian. And more importantly, not only motion control, it also has to continuously align the mirror when observations are going on. Everything has to be done automatically and provide at least an overall imaging accuracy of 0.4 arc second. That means the star wandering on the focal plane because of the error band, etc., should not be more than zero point 0.4 arc second. The diameter in which the star wander should not be more than 0 0.4 arc second. So some parameters of important parameters of the telescope which are used for automating and automatically controlling the mirrors and axis of the telescope are the following. The primary 3.6 meter diameter mirror is supported on 69 pistons, pneumatically actuated pistons. These are axial actuators. They apply force from underneath. And the secondary system is supported on a steward platform, a hexapod system, which actually tries to align with the center of the primary. So it can translate in X, Y, and Z and give a tip tilt motion. So this entire setup is called active optic system, which dynamically aligns the telescope autonomously and provides an image quality better than 0.6. So this is the desired specification, although we are getting much better than this. In the past 2 months, this telescope is being used by Indian astronomers. And although the control system is very precise and tracking pointing is very precise, it doesn't take, the control system doesn't take feedback from the image quality. It only takes feedback from the encoder. So there are some inherent drifts in the telescope because although the axes are orthogonal, they cannot be perfectly orthogonal. There could be some eccentricity, etc. So there will be some drift of the image. So there is an auxiliary guiding system where an auxiliary star is also observed along with the science target at a very fast rate, a few seconds, and any drift in the star centroid is corrected by measuring the centroid drift. The correction is applied to the control system. So this can enable a precise tracking rate of 0.1 arc second. That means the star doesn't wander beyond this circle of diameter 0.1 arc second. So Telescopes are also called robotic telescopes. Normally, these telescopes are very large. The slew rates are very small. It moves at a rate of 2 degree per second. But there are also two robotic telescopes, which are very small for dedicated science survey and all. These are autonomous systems. They can work in a robotic mode. So this particular telescope can be coupled with a scheduler in which all the targets are pre-fed. So what it does is it optimizes the path which target has to be observed first, so that the time of the telescope is optimized, and it autonomously tracks points the objects, takes the images, and does the tracking. This can also be used in a manual mode or with human initiation. Every night, a human can initiate the telescope and feed the coordinates of the objects, and then it automatically points and tracks all these celestial sources. So, along with the telescope is enclosed in an enclosure. The enclosure has an opening on the top through which the telescope can see. This opening runs down up to the horizon. So this is called dome. And when the telescope has to look outside, the dome shutter opens. Since the telescope moves, the dome motion has to be synchronized. The opening of the dome has to synchronize with the aperture of telescope. The dome has to move continuously, and the closed loop position and velocity control system also takes care of other offsets which are modeled and fed as a lookup table. There's also a requirement of thermal control system in the telescope, because heat actually creates distortion in the image, and also it also changes uh, because they have some finite CT coefficient of thermal expansion. So the temperature has to be homogeneous across the telescope. So there's a thermal control system and also a lookup table for aligning based on the ambient temperature. So it takes feedback from automatic weather station. It also interfaces with GPS for exact time reference, so that the sources in sky can be precisely pointed. And it also interfaces with the International Celestial Reference System through internet. So there are many interfaces which assist this autonomous mode of operation of this telescope. And more importantly, there should be a real-time image quality adjustment using automatic alignment of the optics using active optics and adaptive optics system. And there are other support systems like hydraulic control system for supporting the bearings, and pneumatic system for the mirror actuators, pistons, etc. And this telescope can be operated remotely. Normally, no operator sits in the telescope floor because the telescope's floor, the temperatures are very low. It's not very comfortable. And second thing is it's very dark. And third thing is human beings also radiate heat. So we don't want any heat sources near the telescope. So they need to have robust telemetry so that they can be operated remotely, and the telescope system has to be very reliable. There should not be any failure when these are used. Of course, they can be fully controlled, monitored remotely in a manual mode, or can be interfaced with the observatory control system. So ground-based telescopes have several advantages. As I said, the diameter can be really big. Only the technology can limit the diameter. And the cost of ground-based telescopes are just a fraction of space-borne telescopes. The advantage of space-borne telescope are they are very, very accurate. There is no atmosphere, so there is no distortion introduced by the atmosphere. But of course, they cost a fortune to launch space telescopes. So in ground-based telescope, the data volume can be really high. So telemetry is easy. We can have large bandwidth. Maintenance upgradation is easy. And we can always keep upgrading the back-end instruments, the focal plane detectors. So right now we have a couple of spectroscopes one is infrared and one is optical spectroscope. And these are large instruments. They weigh about 2 tons and very accurate. And there are two imagers which are used in telescope. So this telescope has 3 ports. We can select which port we want to use, which instrument we want to use. And already new generation instruments are in pipeline. Integral field spectroscope, which is being developed by uh, AICTE, which is situated in Pune University. And there's a plan to install a high resolution spectrograph and a fast multi-channel photometers. So we can always think of this is actually driven by two BLDC motors. It's a simple gear train. The motors have spur gears which drive the axis directly. So two motors are used to eliminate the backlash by driving the axis in counter torque and counter torque direction. So one motor leads the motion in forward direction, other motor leads the motion in the reverse direction, and tooth contact thus is never lost. So there is no backlash. Again, it has a directly mounted encoder, on-shaft encoder, for getting a precision feedback. So this is the control components of the telescope: direct drive motors, precision encoders, and special bearings. And whenever we do any maintenance, major maintenance, or replace the motor or change the motion controller or drive, so the friction in the telescope has to be characterized, because the motion has to be very, very precise. So we use a Lugre model for friction for characterizing friction in telescope. So here you can see the azimuth axis, which is taking the maximum load of telescope. The torque is very, very less. Starting torque is close to 20 Newton meter. So essentially, two people can easily rotate the telescope with their bare hands. And friction need not be symmetrical. So if you see here, it straight away enters the linear regime of friction. Altitude axis is supported on precision bearing system. Here also the stiction is less, and we operate the telescope. All this velocity range are away from the nonlinear regime of friction, so they are into the linear regime of friction. But the torque is fairly high compared to azimuth axis, because this is not a hydrostatic bearing. There are hydrodynamics when the system moves from rest and comes into motion. Rotator axis has a gear-driven system, so the friction is high, and it also exhibits significant stiction. But again, we operate the telescope in this regime, which is mostly linear. You can see the torque is much, much higher, although the load is less. Because of friction, the starting torque is much higher here on rotator axis. So this is done periodically. Of course, there are electronic compensation technique for friction, but these are not normally used on large telescopes, because large telescopes, they prefer custom off-the-shelf components for implementing the control algorithm. The auxiliary guiding system, which I described earlier, which uses a guide star to control the residual drift, that also has to scan the sky to pick the reference star. So it requires a two-dimensional motion. This is the guiding system which moves around the science field on the annular ring. Central part is the science field, and it uses two axes for scanning the two-dimensional annular annular disk, and there's a third axis for adjusting the focus. So again, it's a three-axis independent system used for the guide axis. The entire control system for telescope, this telescope is very large, and it is installed on a pier, isolated pier, which is above the ground surface. So this telescope is above 8 meters from ground zero level, and it spans up to a height. Tip of the telescope is at a height of 21.5 meter. So most of the control system, they are distributed from ground level to the top, and most of the heat generating elements like hydraulic power pack, chillers, they're all located on ground floor, and the heat is flushed out in prevailing wind direction, so that it doesn't radiate into the telescope envelope and disturb the image quality. So the master controller is located on the ground floor, and the master controller has slave controllers all across the telescope height for controlling various axes. So this is implemented using delta tau UMAC controllers by Omron automation. So apart from motion control, there are several auxiliary control. Both the parameters have to be monitored and controlled. especially the hydraulic unit, liquid control unit, compressed air system, bearing pads, the bearing system, mirror covers, etc. All these IO controls are done by distributed network of PLC. We use BNR PLC here, and the real-time control is communication is implemented using PowerLink network. So this motion control system although gives a precision motion control system, but without mirror control system, we'll have issues with the optics and image quality. So as I said, active optics is there in this modern optical telescope here. So this corrects the slow effects, that is the errors introduced, misalignments introduced due to, especially due to gravity. So the mirror gets misaligned when the telescope is in motion, and the telescope tube also flexes. And the mirror is supported on a mirror cell that also deforms because it's not infinitely rigid, so that deforms. And there's a thermal expansion also. And the mirror, when it is polished in factory, there are also low frequency figuring accuracies on the mirror surface. Uh, Also, there are some wind effects because telescope is open to sky. So the wind loads the mirror and causes some misalignment. So these are all slow effects which can be controlled using a technique called active optics system, which we'll be discussing very soon. So without active optics system, this misalignment will introduce coma in the image. So a circular image can be seen as an elongated comet. It can have astigmatism. So we can see this is the image of Saturn, original reference image. And when there is a defocus or coma or astigmatism, the image becomes blurred. So all this has to be controlled continuously. So what this active optic system does, the mirror actually, primary mirror is supported on array of force actuators. These are pistons. So the mirror can be deformed to change the shape of the mirror, and it can be tilted in both the directions, translated. So when the telescope observes the celestial objects which are meant for science observation, a reference star is also observed, and it's observed at a very fast rate. And the wavefront information from the reference star is generated using the wavefront sensor. So this actually gives the aberrations in the wavefront, and this is fed back to the control computer, and it calculates the force matrix required for removing the aberration. So it applies a array of force on the mirror so as to counteract the aberrations seen by the telescope. So this is the active optics control system, and it operates at a very, very slow rate. So this is our mirror, which is being installed on this array of active optics actuators by our optics group at Aries. The secondary mirror is also suspended. It is supported on Stewart platform. This is mainly used for centering the mirror with respect to the primary mirror. So this is the entire control system for the primary mirror, the active optics control system. As I said, the primary mirror is supported on the pistons with a stroke of 5 millimeter. So this can apply force from 10 to 1000 newtons, and it has a precision piezoelectric valves because these are pneumatically controlled. So these are pneumatic valves. And there are, of course, passive lateral supports also to position the mirror laterally. So all these 69 actuators, they have inbuilt local control unit to maintain this particular force. So they use a microcontroller by Texas Instrument, and they implement bang-bang control. And all these 69 actuators are interfaced with this dispatcher PC, which sends the commands, set point commands to these actuators over CAN bus. So So this is the control system housed inside the telescope, which forms the primary mirror control system, and the secondary mirror is, as I said, is suspended on this hexapod system, which gives 6 degrees of freedom. And there's a separate PC which does the kinematics to translate the telescope generated coordinates into the coordinate system of the Stewart platform. So this is a kinematic single board embedded PC which is embedded into the control system panel of the secondary system. And this secondary system, each pod has a motor, harmonic drive, anti-backlash harmonic drive, and the 6 pods are controlled by a 8-axis motion controller, of which 6 axes are used for this control. There are various other protocols used in this telescope. The motion controller is a master slave configuration because it's a distributed motion controller, and the communication, real-time communication takes place over this optical fiber macro ring structure, and the PLCs, they communicate with each other over power link. They also have special sensors which are networked on this primary mirror system, which communicate over X2X link. These are all the communication network developed by this particular BNR company. There are also non-real-time control because the telescope is operated remotely using a human-machine interface. So there's a telescope control software system, which is a separate PC, which interfaces with the telescope over Ethernet. And since the commands are normally dispatched low compared to the real-time control, Ethernet is sufficient for this kind of exchanges. There's a mirror control PC, which is used for manually controlling the mirror if required and monitoring the status, and also setting the auto guider unit. They also communicate with the telescope control system over this Ethernet interface. So there are various device-to-device communication, PC to PC and PC to hardware communication, which are continuously happening in this telescope. So, as I said, adaptive optics is very important to make the telescope at par with space-borne telescope because it can eliminate the aberrations introduced by the atmosphere, Earth's atmosphere. We don't have this adaptive optic system in telescope, but it will come as a future upgrade in a span of 5 to 6 years on this telescope. So what it essentially does is, this is the image taken by a very large telescope, VLT, European telescope, which has a 8-meter diameter mirror. So when this image is a very closely spaced binary star, one cannot resolve the two stars separately because the resolution is poor because of the blurring effect of the Earth's atmosphere. So when adaptive optics system is used, it can eliminate the effects introduced by the atmosphere and one can resolve the closely spaced objects in sky. So this is the adaptive optics technique. The light which is coming from the celestial source, and also a companion star is selected for getting a feedback about the wavefront aberration. So science object and a companion star both are observed, and the image first hits the deformable mirror and gets reflected through a splitter. So the beam splitter sends the science image to the science camera and the companion star or the guide star image to a wavefront sensor. Because the atmosphere changes very quickly, so this camera is very fast, wavefront sensor system. It immediately calculates the aberrations in the Earth's atmosphere, in the wavefront introduced by the Earth's atmosphere and gives a feedback to the control system. The control system deforms the deformable mirror and introduce a exactly opposite distortions to counteract and get a actual plane corrected wavefront, which can be used by the science camera. So this is just to give an example, a 10-meter Keck telescope which is installed in Hawaii. There is no adaptive optics working here, and this is the image taken by the space telescope. They both image Neptune. So the Hubble Space Telescope, because there is no atmosphere, it can see these sharp features on the surface of this planet. And once the AO loop is closed, even the ground-based telescope can do imaging, which is at par with the HST telescope. So using AO, active optics and precision control system, we can actually have very precision ground-based telescope, which are at par with very expensive space telescopes. So there's a limit to which we can increase the sharpness, which is defined by the diffraction limit of the optics. So this is the physical limit. So the physics govern how what is the best quality of image that can be achieved using set of optics. So a point source, when seen by a telescope, a ideal telescope without any aberration, the point is imaged as a disk of certain radius due to diffraction effects. But the aberrations due to telescope and Earth's atmosphere further degrades this image quality, and the diameter of the point source further increases. So this is the disk of the image seen through Earth's atmosphere without adaptive optics. And with adaptive optics, the light concentration can be increased and it can go closer to the diffraction limited power of the telescope. So just a picture of how complex this adaptive optic system looks. This has several steering mirrors and lenses and a deformable mirror and wavefront sensor camera and some linear guides for for scanning the sky. So the two important components of active or adaptive optic system are the sensor, wavefront sensor, which gets the wavefront information, which gives the feedback of the wavefront aberration, and the actuator, which is actually your deformable mirror. So what this wavefront sensor does is it images the wavefront, the parallel beam coming from the telescope through an array, a two-dimensional array of lenslets. Because it's a parallel beam, each lenslet will image, for example, the star as an individual spot. So all these spots are image of the same star seen through different lenslets. When the wavefront is plane, the spacing is uniform. The distance is equidistant. And when the wavefront distorts due to the tilt in wavefront seen by each lenslet, the stars, the position of the spot starts shifting. So the shifting in XY can be easily related to the slope of the wavefront seen by each lenslet. So now we have a wavefront which with different slopes which are determined by shifting of the stars, and this aberrated wavefront can be further decomposed. So just like Fourier transform, which transforms a time domain into frequency domain, Zernike transform is used by optics engineers to decompose this wavefront into a set of orthogonal polynomials. So each component represents one particular aberration, wavefront aberration in the wavefront. So since these are orthogonal, they can be corrected independently, and a collective correction can be applied using superposition principle. So each polynomial of coefficient of this Zernike transformation, it represents one particular error. So these are low order aberrations which are tip and tilt. If there's a tilt in the image or tip in the image, then it can be resolved using the lower order Zernike terms. And they give information about defocus in the image, astigmatism, coma in the image, trefoil, tetrafoil, higher order coma, and astigmatism. So all these aberrations can be independently resolved. And once you have all the aberrations, we need to have a relation between the aberration and the force matrix so that the force can be applied on deformable mirror. to counteract these aberrations. So this is how a deformable mirror looks. The conventional deformable mirrors used earlier, they were normally implemented on the large secondary mirror. Because the inertia has to be less, the mirrors are thinned. These are normally 1 meter maximum diameter of 1 meter mirrors, and they are thinned to 1 thickness so that they can be deformed. And they are actuated using piezoelectric actuators. Normally, these actuators are very, very bulky, and they are very expensive, and they require large driving power, large voltage, and they dissipate a lot of heat about the telescope. So recently, the MEMS deformable mirror has become very popular in telescopes, and we can use micro MEMS deformable mirror closer to the focal plane, so that small mirrors can be used. And this is a typical MEMS deformable mirror developed by Boston Micro Machines USA. These are very thin mirrors, 2 micron. It's a monolithic thing because it's a MEMS, and it's really very stiff. It can be operated at more than 10 kilohertz or so. It has non-contact actuators. There is no hysteresis. Can take several cycles and consumes very, very less power. So they are available in both segmented and continuous phase sheet configuration. And to eliminate this, always advantageous to have this deformable mirror as a secondary, large secondary mirror, but they are expensive. And since it dissipates, it has several disadvantages. The European community is also working on developing a deformable, large deformable mirror using a voice coil technique, so that there is no dissipation of heat, and it eliminates all these disadvantages. But again, this is very, very expensive. For simple adaptive optics, one prefers MEMS deformable mirrors. They are very cheap. So that is the actuator which applies the correction, and we need to model this deformable mirror before it can be used. Generally, these mirrors come along with their own set of controller which can be tweaked, but they can also be modeled if one plans to custom build deformable mirrors. So these mirrors are, the deformations are very, very less in nanometer compared to the thickness of the face sheet. So they can be treated as thin plates, and thin plate technique can be used for modeling this deformable mirrors. So the deformation W can be related to the force, and the applied force again can be represented, because these are point loads. They can be represented using two-dimensional Fourier transform, and a solution called Navier solution can be worked out to get the solution of this deformation. Of course, we require boundary condition, so we use the simply supported boundary condition here. Generally, the deformations are normally known in advance because they are measured using wavefront sensor, and we need to calculate the forces, matrix of forces which are to be applied to the mirror from underneath. And since it's a Navier solution, so one can use superposition principle to get the overall deformation as a result of applying the point loads, matrix of point loads. So we need to determine the force given the deformation. So it's an inverse problem, and so there's a derivative term involved here. So whenever there is high frequency noise in measurement, it worsens the force determination. So there is a way people use truncated singular value decomposition, but people also use regularized solution so that it weighs the coefficients as a using a regularized filter term. So here just simulated when there is a noise which is 1/10 of the deformation, the force determined using the inverse matrix is noisy, and using the regularized solution we can actually get the real clean force representation. And when this is applied, to the mirror, the deformation shape matches the actual shape of the theoretical shape of the deformation. So this is just one technique which can be applied for controlling the deformable mirrors. So overall, this is the adaptive optics scheme where the science object is observed through atmosphere and a companion reference star is also observed simultaneously through this same patch of atmosphere. And the wavefront information is extracted from this reference star using wavefront sensor, and correction is applied using control system using a deformable mirror so that we get a plain wavefront at the science camera end. I'll just skip this slide. So image quality of the telescope, before understanding how this is improved, we need to understand the image quality of the telescope. Telescope resolution is defined as this equation 1.22 lambda. Lambda is the wavelength of interest divided by the diameter of the telescope. So larger the diameter, better is the resolving power of the telescope. And uh, so this is the actually the diffraction limit of the ideal telescope. That is, when you image the point source using a telescope or the optics, the size of the image will have a finite diameter. So the angular size of the image is given by this formula. So astronomers call this FWHM, full width half maxima of the PSF, and the normally the telescopes have FWHM of 1 arc second, good telescopes, which can be improved by again mirror control techniques to 0.5 arc second or so. So the improvement is measured using Snell ratio. So the actual peak intensity of a diffraction pattern compared with the peak intensity of the actual image of the star imaged by the telescope, the ratio is called Snell ratio. The higher the Snell ratio, better is the quality of the telescope. So if we have to apply adaptive optics in next 5 years, the atmosphere also has to be understand where the telescope is installed, and the turbulence characteristics have to be characterized. So the atmosphere is highly turbulent because the energy is continuously injected into the atmosphere on a larger scale, and these larger scales are termed as eddy, and this eddy cascades into a smaller and smaller scales, and the smaller scale is dissipated into the atmosphere. Energy is dissipated into atmosphere due to wind drag and all. So this turbulence model has to be determined to actually implement the adaptive optics scheme. Uh, so this image actually shows the variation of the temperature in the atmosphere. So the temperature actually decreases long and up to the tropopause, the temperature actually inverts. And again at the tropopause, this inverts back. So this is called the profile of the temperature at particular site. So this profile of the temperature has to be known to know the fluctuations which is induced in the refractive index of the air column. So this is the Kolmogorov turbulence model, which is very popular in the atmospheric science. They characterize the atmosphere turbulence using Kolmogorov model. So simply to understand this, as I said, the largest eddy will have a scale of say L0, and it is dissipated, cascaded into smaller and smaller eddies. So the scale R naught is the size of the patch of the air column where the wavefront is homogeneous. That is, the refractive index is homogeneous. So this R naught lies somewhere in between L naught and capital L naught and small L naught. So we have to determine what is the patch of uh, the atmosphere where the refractive index is homogeneous. So this R naught is called Frit parameter. So this is the diameter of the wavefront where the wavefront aberrations are very, very less, one sixth of the lambda of the wavefront of interest. So this is also called coherent length because the wavefront is coherent here. There are no aberrations in this patch. And this patch also changes with time. So how fast this atmosphere changes, so how long the atmosphere remains homogeneous, this is characterized by the coherence time. So the coherence time is dependent on the coherence length R naught and also the velocity, the wind velocity at that particular layer. So we have to know both the coherence time and coherence length. So we need to know what is the patch for which the correction has to be applied and how fast that correction has to be applied. So this was previously characterized at our site, and we find that the R naught, the coherence length, that is 10 centimeter patch of sky, it remains coherence. So if this is the wavefront, so every 10 centimeter is homogeneous. The wavefront refractive index is same. So when you cross this 10 centimeter, again the refractive index changes. And this also changes with time. So the atmosphere remains static for 3 milliseconds. So all the corrections have to be done at this rate, faster than this rate. Then there is a third parameter which has to be known, which is called the isoplanetic angle. So how far this companion star can be away from the sine source. They should not look into two different wavefronts, two different columns of atmosphere, because the correction applied from the reference star to the sine star should not make the situation worse. So it has to be very close to the science target so that they are seen through the same air column, and the aberrations in both the air columns are same, both the wavefronts are same. So this again depends on the coherence length R naught and height of the atmosphere. So if you want to apply correction to a height of h, then the separation of the reference star from the main star is given by this formula. So again, we have characterized the coherence isoplanetic angle for our site, which is close to zero 0.6 arc second. We have another site where we have an older telescope where the isoplanetic angle is less. It is 0.6. At Devasthal, it is better. It is 1.4 arc second. So we can select a star which is separated by an angular separation of 1.4 arc second. So by applying this adaptive optics correction, even if we are able to remove the lower order terms, that is tip tilt and lower order aberrations, we can eliminate 70% of the wavefront aberrations. So normally the adaptive optics is implemented in phases. Simplest tip tilt correction, that is just to tip and tilt the mirror to collimate the photons close to the centroid, that itself can give you a very good imaging accuracy. So you can see this spread in light when there is no adaptive optics, and just by applying the tip tilt adaptive optics, we can get a very good PSR, which is closer to the diffraction limited image. So beyond this, higher order corrections are applied where you require a deformable mirror for removing the higher order aberrations. So this mirror control adaptive optics technique, is it very successful, and how useful it is? As I said, the angular separation between the companion star, reference star, and the sine star should be very less, and the probability of finding such a bright star, always finding a bright star close to the sine star, is almost negligible. So one has to go for an alternative, and when we use shorter wavelengths, the aberrations are more. I mean, the R naught, the Frit parameter, the patch of the atmosphere where the refractive index is homogeneous, it is linearly proportional to the wavefront, the wavelength of the interest. So larger is the wavelength, you get a larger patch where the wavefront is homogeneous. So it is good for infrared, not very good for visible light. And we require a large degree of freedom if your coherence patch is very, very small, because if the pieces are very, very small, you need a greater degree of freedom for deforming the mirrors. So people use adaptive optics for larger wavelength like infrared, and they use artificial guide stars because the probability of finding companion stars are very, very less. And nowadays, people are using advanced multi-conjugate adaptive optics, where multiple adaptive optics are used to get pieces of wavefront information in the overlapping region and generate a 3D tomography of the wavefront at different heights and apply the corrections. So they use multiple wavefront sensor, multiple deformable mirrors. It's a very, very complex system, normally used on large telescopes. So this is more or less about adaptive optics, advanced mirror control techniques, which is now very, very essential for large telescope for getting close to diffraction limited imaging, which are at par with space telescopes. So to support this motion control technique and to also plan for upgrade, because telescopes run for 40 years and every 10 to 15 years we have to upgrade all the control systems. We also need to understand the algorithms, develop new techniques to eliminate the issues which are found earlier. We have a development lab in the electronics building where we have a replica of the telescope panel which was built here, and we have test linear stage and precision rotary stage which has a encoder of
I think speaker has disconnected, so we'll wait for him to join or reconnect.
Hello.
Hello, sir.
Yeah, I'm sorry.
Yeah,
There
yeah,
was
yeah.
some internet outage, so I had
Hmm.
to shift the room, change
Yes.
the room.
Now it is visible. Screen is visible.
Yeah. I was at this slide and it got disconnected.
You're, you're on. Okay. Okay.
Okay. So, this was more or less about the adaptive optics system. So, to support this motion control activities in the electronics lab, we have a development facility. So, where we have developed a motion control panel for the telescope. So, this uses the precision motion controllers and drives, and there are linear and rotary stages with precision encoders and provision to add inertia, change the imbalances, etc. Validating and learning all the control techniques, because every 10 to 15 years these control systems are normally upgraded on the telescope, because the life of telescope is close to 40 years. So they are, it's a continuous process where this is done. And for validation, we have several tools. Mostly it is MATLAB simulation to begin with, and there are techniques like processor in loop and software in loop techniques. And there are platforms like DSpace, where the hardware in the loop simulation can be done. And there are some processors by Texas Instruments, which again can be interfaced with MATLAB Simulink. And many intern students, they also do experiments. They try to build low-cost controllers using these processors and compare the performance with the precision delta motion controllers. So this kit has linear and PWM drives and BLDC DC motors, where these techniques can be evaluated. And there are precision tools like multi-channel, eight-channel mixed signal oscilloscopes of high bandwidth, and several function generators and precision meters and power supplies, which can be interfaced with PC and continuously logged for measuring the parameters. So once validation is done, we also have some evaluation platform. There's a small telescope. It's a real telescope with optics and all, and it has a dome through which the telescope can see outside. So this is equipped with precision encoders, incremental and absolute encoders, on which this low-cost or homegrown controllers can be tested, and also the upgrade hardware which can be planned for telescope, they are evaluated on this platform. So students, they come from different universities. They try to do experiments and learn these techniques on real platform. So I would also invite your group, the enthusiastic students and faculty who would like to collaborate and participate in these activities at ARIES, where the control system and optics control system, these things can be learned, and they can be developed. So that's more or less about my talk, and thank you very much for your patience. And if there are any questions, I'll be very happy to take up.
Thank you, sir. So are there any questions from the participants? Sir, what are the most, again, we have to consider the most important features of robotics telescopes?
Yeah, so this telescope, as I said, they are robotic because they have to work autonomously. So all this correction, mainly the motion control control system, which provides a very stable platform for the optics. That is very important. Unless that is precise, we cannot have advanced control techniques like mirror control techniques. So after that, the mirror alignment has to be done continuously when the telescope is running. So we require precision adaptive optics and active optics techniques. One is used for aligning the optics. The other one is used for compensating the aberrations introduced by the atmosphere. So these are the important aspects which are required.
Thank you, sir. Sir, one more question is from the participant. Are we using PLC for controlling everything? Can we use microcontrollers?
No, PLC is not used for controlling the motion here. PLC is used only for IO-based control, for monitoring the auxiliary systems and all. Because motion control uses with high resolution encoders, and although it is a PI controller, it also requires additional phase lead lag compensator and a notch filter, series of notch. So it is used. So for motion control, we use delta tau motion controllers. These are mainly used in CNC machines developed by Omron. And for simple motion controller can be used for smaller telescope, like I showed in the end of the slide, where the students, they try to use the more interesting microcontrollers by Texas Instrument and Microchip, and they develop very interesting distributed controllers. So that can be done for smaller telescopes.
Okay. So can you highlight some of the research areas in this field?
Yeah, research area is mainly the precision control, because at low speeds there are various challenges which pose control related problems. One is friction. So one has to identify the friction and try to compensate it. And when such large structures are built, your theoretical model, it doesn't work actually. So you need to use system identification techniques to get the pole zeros of the system, behavior of the system, and approximate it to the closest possible linear transfer function model of the system. So that is one thing. And for adaptive optics and active optics, it's very challenging because it requires multidisciplinary aspects. Software is one. The hardware has to be very, very fast. So real-time processors and GPUs are used for calculating the wavefront aberrations. Controlling the deformable mirror is totally another field where it has to be modeled as a thin plate using thin plate theory, and control algorithm has to be developed. So it's very challenging. And of course, there are a lot of software now which are used in telescope, like artificial intelligence, to automatically scan the sky, identify various triggers, various sources, and generate triggers for the companion telescopes. So these can operate in survey mode using AI. So this is one of the things which we'll be implementing in our new 4-meter class telescope, AI and machine learning. So these are various interests, research interests one can pursue in this telescope. Yeah.
So instead of reflective mirrors, can we use that software for adaptive optics? Yeah, that is.
Reflective mirrors are required for collecting light from celestial sources. So mirrors are basic entity of telescope. There is no substitute for mirror. They are very expensive. They cost. So this cost of the telescope is about 150 crores, and out of which 40 crores goes only for the mirror. So it's a artificial intelligence is used for building the intelligence in the system to efficiently scan the sky and efficiently apply the corrections.
Okay, thank you, sir. So one more question is from Mohsin Dalvi. How tight are the tolerances in robotic structure of telescopes as compared tolerances in industrial robots?
Industrial robots only for semiconductor industries, where they use nano positioners. But these robots are very, very small, which are used in semiconductor industries. Generally, manufacturing robots, which are used for welding and assembly, their tolerances are very high. They don't require very precision tolerance. In case of telescope, because we talk in terms of fraction of microradians, and also it's a very large structure. So the precision and is very high. The control components are extremely expensive. The encoders are very expensive, and we cannot have any backlash and other errors. So special motors are used to directly drive the telescopes. In principle, they are same, but the technology which is required for the precision, implementing the precision, are very of high standards.
Okay, thank you, sir. So one more question, last question, like from S. Khandekar. Are there any simulators available to check our lab results with actual results?
Yeah, so if you have a model, you can always do a processor in loop simulation and compare with your, for example, MATLAB gives this provision. So these controllers which are used in telescope, that can be interfaced with Simulink. So you can run the same model on the processor and also your system, and you can compare how precise is your modeling. And for validation, for building the hardware, again, you can use hardware in the loop like DSpace. Again, we have this here. And normally, even if it is validated, it is not directly implemented on telescope. We again require a test platform. So we have a smaller telescope on which you can actually play around and implement new techniques.
Okay, thank you, sir. So, are there any further questions, or we can? I will say the vote of thanks. So, on behalf of Department of Electronics, I would like to sincerely thank Dr. T.S. Kumar for sharing his valuable time and knowledge, as well as motivating us. All of us are always fascinated by telescopes, and thank you, sir, for highlighting on recent developments in the area of optical telescopes. So indeed, it was a very informative session on how to precisely control these automated optical telescopes. So I'm sure everyone would have benefited from this talk. So with this positive note, I would like to conclude the session. Thank you, Dr. T.S. Kumar, sir, and thank you, participants.